Hi, so we're going to continue by looking at another example of joint distribution to try to help solidify these ideas in a much cleaner way. So what we're going to do is we're going to look at the previous example, the one from the last video, and kind of look at it in a different way. So this time what we're going to do is we're going to say we have one bag with 3 marbles and 1 blue marble. Let me highlight the green. And I pull out 2 marbles. So I'm pulling out 2 different marbles. But I'm saying that I'm doing this without replacement. So remember when I say without replacement, that means I pull it out and I leave it out. So what I'm going to do is, in this case, the event is going to be given by I pull out marble X and then I pull out marble Y. So let's kind of see what happens. So first I need to pull out X. So the first chance if I pull out a red, so here is bag 1, right? So I have 3 reds and 1 blue. If I pull out a red, my bag is going to have 2 reds and 1 blue. So here I'm drawing a tree diagram, right? Kind of. It's not really a tree diagram, I guess. And then if I pull out a blue, then I'm left with just 3 reds. So if I pull out a red first, well, in the first bag, I have a 3/4 chance of pulling out a red. And then what's the chance of pulling out a red in the second turn? Well, in the second bag, so I come down this way, I'm in this bag here, so I have 2 reds and 1 blue, so I have a 2/3 chance. So this is 2/4. So it's roughly 1/2, right? I guess I'll just keep 2/4. The 3's cancel. Okay, let's look at when X is equal to blue. So if X is equal to blue, well, I'm going to put out a blue, so I have a 1/4 chance of this. And then I multiply by the chance of pulling a red. Well, I have 3 reds out of 3, so I'm going to have 3 out of 3. So it's multiplying by 1, so I get 1/4. And as we saw in the last video, I can look at what happens when Y is equal to red. So what's the chance of pulling red the second time? And in this case, the chance of pulling the red the second time is just the sum of these. So I have 1/2 plus 1/4. This is just 3/4. So the chance of pulling red the second time is 3/4. Okay. Let's look at, if we look at the blue side. So if I pull out a red first, X is equal to red. So again, I'm going to have 3/4. But this time I'm going to look at blue. So I'm going to multiply by, in this first bag, I have 1 blue and 2 red. So I have 1/3 chance here. The 3's cancel, and I'm left with 1/4. I guess I should make these black. And then in the last one, I start off with 1 blue, so this is 1/4. And then I want to pull out another blue, but I don't have any blues in the second bag, right? When I pulled one out. So I end up with 0/3. And so basically 0 times anything is just 0, so I'm going to be left with 0. Let me do this in black. And this allows us to basically do all the summations. So 1/4 plus 0 is 1/4. Here, if I look at the column X equals red, I get 3/4 just as before, then 1/4. And you can see adding up each thing gives me 1. So the cool thing is, if you look at any individual row or column, you're going to see we get the very same thing as this little part here, right? This is the same. But the inner part is different. So the distribution inside is different, but if you look at any particular pulling out, so pulling out a red second or pulling out a blue second is going to give you the same probability as just using a second bag. But the distribution of the 2 joint distributions are the same. So looking at our 2 examples, what we might notice is that these totals on the right and on the bottom are identical, right? Like this 3/4 and 1/4, right? So if we look at, let me write this out a little. So I have this 3/4 and 1/4 here. This is going to be identical to the 3/4 and 1/4 we had here. No, this is not what I want to say. What I want to say is, sorry, if I look at the 3/4 and 1/4 here, and I look at the 3/4 and 1/4 here, there we go. That's why. Then what we'll notice is that they're identical, right? 3/4 and 3/4, 1/4 and 1/4. And we have the same thing for this last one as well, right? We have 3/4, 1/4, and 3/4, 1/4. Now this is something that doesn't always happen, but when it happens, we know that the two random variables basically have the same distribution, right? So x red is 3/4, x blue is 1/4, y red is 3/4, and y blue is 1/4. So but they basically have the same distribution. It's not that different. And so we say that two random variables are equal in distribution if we have exactly that. If we have that the p of x is equal to the p of y for every x. So it doesn't matter what I put into x. If I put the same thing into y, I should get the same thing. And if that occurs, then we say that they're equal in distribution. And the cool thing is, if something is equal in distribution, right, we can just change the little standard variable to whatever we want. So I can always say, like, I can make x squared or something. And this will be the same thing as well. So it's pretty cool to have things that are equal in distribution. It lets us know a lot of things. But what about when two random variables are actually equal to one another? They're identical to one another. Now this is a little more complicated in the sense that it's a little harder to see right away when you're looking at this. And basically what we'd want to do is we want to say that x is equal to y. But this doesn't really make sense, right? Because we're looking at probabilities and we're looking at events. So really what we should say is that the probability of x is equal to y is equal to 1. And that really gives us what two random variables are equal. Now this might not make any sense, right? This you might like, I don't get how this, like, I don't get this. So another way of saying this is if I look at my distribution, or if I look at this probability, remember from last time, we can kind of set this up as, this is massive. We can set this up as a summation over all y. So we kind of saw that, where was it? Here, in blue, right? So we kind of saw this. And what this means is I can make x be equal to y, and I can add my y's in, right? Well, here I'm basically saying what the y is. Y is equal to little y. So let me change that. And notice how we said this has to equal 1. And so that's kind of a different way to look at it. It's basically saying if you take the sum of all the things, then they have to be equal to 1. So if we're looking at the table, the best way to kind of think about this, the way I think about this, is I look at the table and I look at for two things. So I say equal in distribution is basically saying that the right column and the bottom row are the same. They're identical, like they do the same things in the same order. Equal is basically saying that the sum of the main diagonal, if I go through the main diagonal and I add everything up together, then this has got to be equal to 1. That is the main difference between the two. So we have equality. How about, so if we have this equal sign, but rewind. So we have this p of x equal y. So can I do something like this with just anything? Like any symbol? And we actually can. How would we say p is if x is less than y? What happens if I want to say that the random variable x is less than the random variable y? Well, let's just do the same kind of dumb thing. We'll say all y. We'll say p of x less than y. And then we say y is equal to y. And this, of course, is going to be the same thing. We just set y equal to y. So that's cool, but we can go even further. We can look at x plus y is equal to z, for example, right? So let me try this. Let's try the same thing. So we say all y. We'll look at x plus y equal to little z. Y is equal to y. So here we have all y. P of x plus y equals z. Y equal y. But here, I know this formula, right? I can just subtract y from both sides. So this is just all y. P of x is equal to z minus little y. Y is equal to y. And notice here this is something we can do. So this is actually pretty nice. We'll use this in, how long has it been? We'll do a quick example, and then we'll cover the final topic in the next video. So we're going to look at a quick example, calculate this distribution. This we've already done before, actually. So we want to calculate the distribution of x plus y if we roll two fair-sided, six-sided die. So this, what we're going to do is, first we're going to write down the normal distribution. So we'll let x be first die, be rolling a first die. Y is second rolling. And so if we create a table, let's create a table. We'll put y here and we'll put x here. X can either be 1, 2, 3, 4, 5, 6. Y can be 1, 2, 3, 4, 5, 6. Now, if you think about this, if I take any of these numbers, right, so we'll start off with 1. This is 1 over 6 chance of rolling a 1 for the first die. This one is also 1/6 chance of rolling a y for the second die, because these two are independent rolls, right? So I'm rolling two fair die. They're two fair dice. They're independent, so they're not dependent on one another. So I'm going to multiply them together because they're independent. So I get 1 divided by 6 times 1 divided by 6 is equal to 1 over 36. If you think about this for a minute, we're going to get the same thing everywhere. We get 1 over 36, 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 etc. So it's all the same everywhere. Little dots. They're all the same everywhere. If I add up any of these rows total, notice how I get 6 over 36, right? There's 6 of these in each. Oh, scheiße. Total. I'm going to remove this before I screw this up again. I'm going to have 6. You black. We're going to have 6 different entries. So that's 6 divided by 36. That's 1/6. And if you think about this a little, we'll end up getting the same for each of the 6 options. And it's the same here. So notice how this one, x and y are equal in distribution. But x and y are not equal. Why are they not equal? Look at the column, the diagonal. The sum is not equal to 1, right? The sum of the diagonal is equal to 1/6. So they're not equal. So this gives us the distribution of x and y. So what is the distribution of x plus y? So this is given by p of x plus y is equal to z. And we want to look at all the different things from before. So let's see kind of what happens if I do p of x plus y is equal to 2. So this, if you recall, is basically when we're saying that we roll 2 1s. So this is roll 2 1s. Roll 2 1s. Right? So if we look at my distribution from here, there's only one thing that gives me this. It's this little chart here. So x plus y is just 1 plus 1 is 1 over 36. So this is equal to 1 over 36. How about p of x plus y is equal to 3? Well, I can either have 1 plus 2 or 2 plus 1, right? These are the two different ways. So if I look at my thing from above, I have this one here, and I also have this one here. So I have this kind of, these two here. And it's 1 over 36 plus 1 over 36. And so we just add them together, which is equal to 2 over 36. And if you kind of recall, I won't go through all of these, but like for example, if I were to take p of x plus y is equal to 7, I would look at 3 and 4, right? So I would look at whenever two things are equal to 7. And in this case, I would get this one here, this one here, this one here, 4 and 3, 5 and 2, and 6 and 1. Obviously, these numbers aren't here because I just didn't want to copy this a million times. But I would do this 6 times. Yeah, there's 6 of these. So I would get 6 over 36, which is 1/6. And so this should give us the same distribution as we saw way back in the day when we looked at the same thing. So we'll end this video here. We'll do another quick video for conditional distributions in the next video, and that'll be it for this week. So I will see you in the next video. Sorry that this one was super long. I know this topic is confusing, so we'll definitely go over examples for this in the problem session. So I will see you then.